Wonderful. There we go. Okay, now recording. So let's get started. So we're extremely happy to have Matthew Baas here from Stellenbosch University, Department of Electrical and Electronic Engineering, doing his PhD. And he's going to be telling us about some seemingly very simple methods for doing voice conversion. So over to you.
Cool. Yeah, so I'm just going to go over some of the recent work we presented at Interspeech last week. And in DARPA-X earlier. And essentially, it's just a simple way to do voice conversion that has some fun applications. So essentially, voice conversion, for those of you that don't know, is when we essentially want to convert a recording of someone so that it sounds like someone else is speaking, but the words spoken must stay the same. So, for example, you might want to convert your voice into Obama's voice or something like that, but the words spoken must stay the same. And this is a couple of uses. We can use it for like fixing people's stutters, or for just entertainment. If you're making a game and you want to diversify the audio in the game, there's a couple. So to give you an idea of what it might sound like, we might have an input recording that sounds something a bit like this. Can you hear this?
A narrow channel formed.
Sorry, see if I can mute myself here.
Yep, we could hear that.
A passage through the ridge of rocks that protected it from the open sea, and which, even in the roughest weather, would ensure the calmness of its water. A narrow channel formed.
So if we have input recording like that and some reference recording that sounds a little bit something like this. Can you guys hear this? It's just not playing.
No, we couldn't hear that one.
Somehow, of all the days when the home feeling was the strongest, this day it seemed as if she could bear it no longer. Somehow, of all the days when the home feeling was the strongest.
So then an ideal output should be this voice, the voice of the female speaker, but saying the same words to input. So it might sound something like this in an ideal case.
A narrow channel formed a passage through the ridge of rocks that protected it from the open.
So that's basically voice conversion in a nutshell. And typically, voice conversion systems are broken up into these three blocks: a feature extractor, which converts speech into something which is more easily modifiable and easy to work on; a conversion model, which does the actual conversion, takes in some indication of your target speaker; and a vocoder, which converts whatever representation the conversion model gives you back into a waveform we can listen to. And that's the typical setup of voice conversion models. So essentially, let's look at each of these blocks in turn. The first one is this feature extraction block. Here, for any of you that have done speech processing, you'll be very familiar with this. And a very common one is to just convert speech into a Mel spectrogram. And this is, for those of you that don't know, it's essentially you chunk up speech into little segments, and you compute the FFT of those segments, the fast Fourier transform, and you kind of stack those segments together, and you rescale the axes to be close to how humans perceive it. And it kind of converts speech into an image, basically, which is much more compact representation. So this is what people used to use, but these days people use even more weird things called SSL model speech features. And this is self-supervised learning model speech features. And essentially, there have been fairly large models in speech, which essentially just try to learn low-dimensional representations of speech. So in this case, we use WAVLM, WAV2VEC, for those of you that know speech models. And essentially, it converts speech into a single vector for every 20 milliseconds of speech. And these vectors have special properties. They're like linearly predictive of the speaker and the words being spoken and a few other things. But it essentially does a similar function to a Mel spectrogram. The key thing with this is that when we do this vocoding, that last block, that either takes in a Mel spectrogram or these speech features and converts it back to a waveform. Training this is very simple. This typically is also either pre-trained model or it's just the digital signals processing output to get a Mel spectrogram. And please, anyone, feel free to stop me anytime if you have questions. In a vocoder, you just have these features and the target, you can just train it. So it's very simple. Typically, most models, voice conversion models, aren't even involved with training. The key insight here is that these self-supervised speech features, linear distances between them correspond actually to different sounds, different speech sounds, different phones. So in other words, I'll explain that in a little bit. We'll get back to that. And now this main conversion model here, this is the core voice conversion model. When people talk about, I've got a cool new voice conversion model, they're talking about this conversion model typically. And new models tend to work in any-to-any settings. And this means that our source speaker and our target speaker can actually be unseen during training. They can be from any domain and even different languages. The main problem that we've seen with existing models is that they're complicated, and I'm not because they're too complicated, and they're a bit hard to work on. So what we tried to ask is there actually a simpler way to do this? Because if we look at some existing conversion models, like this is FreeVC from 2022, it's some fancy flow model. If we look at VQVIA-MC, it's some weird, complicated diagram with different encoders and decoders and mutual information. Or even your TTS is a very recent high-performing model. It's got a lot of moving parts. This is quite difficult to build on and actually improve and tinker with yourself, because now you have to be familiar with all these different components. So we asked whether we can do this in a simpler way, and we try to make use of a key fact here is that these self-supervised speech features, they have this nice property here where linear distances corresponds to useful things. So WAVLM, this is one such SSL model. Again, it just converts waveform into a vector for every 20 milliseconds of speech. And the key thing to note here is that linear distances between these features correspond to similar phonetic information. So if I speak some sentence and I trim out a little bit of where I say the B sound, and I have a bunch of other vectors taken from recordings of you or from like Obama or someone, I just shuffle those vectors together and I find the nearest vector. That nearest vector will be Obama saying the B sound. It'll be the same phonetic information. But critically, it'll be the same phonetic information, but different speaker information. And this is just a linear distance, a linear cosine distance. Does that make sense, everyone, more or less? Cool. So with this key thing that linear distances actually find the nearest same sound from another speaker, we asked, do we really need a complicated model? So because of that, we actually just proposed this model, K nearest neighbors. That's not a new model. Everyone's seen it. This is our voice conversion model.
Sorry, can I just ask there?
Yeah.
With that, with the model that you're talking about in the previous slide, does that not mean that you need to have a fairly comprehensive set of phonemes from the target speaker? Yes. Mm-hmm.
So these aren't exactly phonemes. They're kind of like phoneme-like units. Okay, sure. 20 milliseconds. So it's often subphoneme.
Sure.
I'll tell you a bit later on how much data you need. You can imagine if you've got only 5 seconds of data, you don't have full phoneme coverage. It's not going to work, and it won't work. So I'll show you the trade-off there, how much you need in a bit.
Great. Thank you.
And so this is really our model. So essentially what we do, we have our source speech, we have our reference, from our target speaker, and we take both of them, convert them to these SSL features using a pre-trained WAVLM model. We don't touch it, we just grab it from online. And then for every source vector, we just find the nearest neighbor from all the vectors from the reference speaker and just replace it with that nearest neighbor. And then we just concatenate all of those replacements together, getting this output feature sequence, and we just vocode that back to a waveform using just a pre-trained vocoder. And that's the entire model. So we don't exactly replace it with the nearest one. We find the K nearest neighbors, and we just take the average. It's K nearest neighbors regression. And this is our model. And that audio you heard from the first, from the first slide, that is actually from this model. So I'll try to play this again.
A narrow channel formed a passage.
Yeah, so that sample from
somehow,
the first page is
of all the days when the home feeling was this,
is actually from this model. So this is produced by our model.
A narrow channel formed a passage through the ridge of rocks that protected it from the.
Can I ask another question there? So you said that you find the K nearest neighbors and then you take the average of them. Okay, so essentially here you're just finding those that are within a certain distance and taking some mean over those particular ones.
Yeah, if K equals 1 also works, so it can just be the nearest one. It just works slightly better if you use K equals 4. But as a simplest baseline, just replacing it with the nearest one, in other words, k equals 1, that also works perfectly fine. You get really good sound outputs with just that.
Are there sort of different parts of that phoneme space or subphoneme space where k equals 1 or k equals 2 or k equals 3 work better? So can you actually optimize in some way over the different regions of the space?
You can. So largely for the experiments we did, we found it doesn't matter too much. So in other words, your performance doesn't vary drastically, just slightly. But typically, if you've got a smaller reference set, then you want to use a lower k, because you can imagine if your k is too big, you're going to select phonemes that are actually different from the one you want, because there's not enough of those in your reference set.
Sure.
But if you have a lot of data, like an hour, then even if you make k like 50 or 100, they'll also be the right phoneme, and you'll probably get a smoother representation. So typically, it doesn't make a lot of difference. We tried with, anywhere from 1 to like 150. The sound difference wasn't too bad unless your data was quite limited. But you can optimize it slightly.
Cool.
And the one small caveat here, so this works perfectly fine. And, this half-hour GAN is simply, when we train this half-hour GAN, we simply take, a sequence of Waveland features and the audio corresponding to it, and just train a model to go from the features back to audio. This is, standard vocoder converts a spectrogram back to an audio. We just convert the features back to audio. Nothing too fancy there. But the problem here is that at inference time, each of these features are actually selected from different parts of our reference. They just, we literally stitch them together from different parts. So they can have different, pitch information in them and different other things. And this leads problem to boundary artifacts. We get this weird boundary artifacts from stitching these things together. So then a solution that we came for this is to actually, when we train hi-fi GAN, to train it in the same way that we do inference, where the inputs have been constructed from stitching together different parts of the output. So to do this, we do this thing called pre-matching. And essentially what we do is when we train hi-fi GAN, we don't just go from features to the audio. We don't just go from Waveland features to the audio. We actually first replace each feature with the nearest feature from the same speaker, just from different utterances from the same speaker. And this is purely so that when we do the vocoding, we train the vocoder, this hi-fi GAN, that each feature is already constructed from stitching different inputs together. So that the hi-fi GAN learns to smooth out any boundary effects that are there. This isn't necessary. It still works really well without it. It just gives you a small performance boost on top of that. And essentially, this is just some of the comparisons in the paper to other models. Those other weird, complicated models that have lots of moving parts. There's EuroTTS, FreeBC, and the key metrics we look at here are word error rate and equal error rate, or probably more relevant to humans is MOS and SIM. MOS is a subjective listening score. So here, these two are actually subjective listening scores. So we ask a bunch of listeners, rate how realistic it sounds on a scale of 1 to 5. That's what these numbers are. And then SIM is rate how similar it sounds to the desired target speaker on a scale of 1 to 4, sorry. And you can see that we have similar naturalness, similar realism to existing models like FreeBC and your TTS, but we actually are way more close to the target speaker. And this makes sense because that output feature sequence is constructed only from features from the target. There can't be any leakage of source speaker information to it because the output is only consisting of target features averaged over different times. So basically, we have similar naturalness, intelligibility to existing methods, but our superior similarity, but most importantly, are much simpler than these existing methods. And the cool thing is now, because it is just a simple k-nearest neighbors, if we look at the design here, we never assumed this is even speech. This could be music, this could be whispers, this could be things from other languages. So we can do all sorts of weird things here. So for example, first thing, all those models, the hi-fi GAN, the Waveland, they've only seen English. So we can actually do inference on cross-lingual conversion. So our source can be something like this.
Hanake hatte allen Körperschmuck, den ein japanisches Mädchen.
So that's our source utterance. We want to be staying German, but our reference can now be something
この前
in
探ったと
Japanese.
きは途中に反根の隆起があったので、ついそこが行き止まりだ
So remember, we want now the output to sound like that Japanese man, but he must be speaking German. That's the idea. And none of these models have ever seen Japanese or German.
Hanake hatte allen Körperschmuck, den ein japanisches Mädchen sitzend, trippelnd und liegend zeigt.
So yeah, that's quite cool. And then, we can do a similar thing with whispered conversion, where we convert a full-on music clip to whispered version. So if our input is this, so this is our source.
Creeper. Oh man. So we back in the mine, got our pickaxe swinging from side to side.
And our reference is someone whispering a passage like this.
Ranging over some 1,200 years of poetic achievement, the Imperium Anthology of English verse presents the greatest poem.
Then the output, you can imagine what it's going to be like. It's going to be someone singing in a whisper, and it's actually even going to convert a bit of the background tune with it.
Oh man, so we back in the mine, got our pickaxe swinging from side to side, side to side,
Yeah, and then there's even a more fun thing. We can go even further out of bounds and convert a human to animal. So if our source sounds like this, so we want to convert that to a human, right? So we have our reference, that's now this human female speaker.
At once the goat gave a leap, escaped from the soldiers, and with bowed head rushed upon the Boolooroo.
So what do you think the output's going to sound like? If you had a guess. It's going to be, so we want it to be the same content as the dogs, it must be the same barks, but it must sound like human barking now. So this is what the output sounds like with the model.
Wah, 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 wah.
Yeah, so basically that's some of the fun things you can do. But there's actually a bit more that we can do. So if you remember back here, these are high-level features. So what we can actually do is if we have two target speakers that we want to convert to, we can convert it to one target speaker, getting one set of output features here, and convert it to another speaker, getting another set of output features here, and then actually linearly interpolate, just piecewise by piece, by each vector, just linearly interpolate it from one to the other to smoothly actually change between two voices. So what we can do actually to do this, when we do this, we actually can smoothly go from one voice to another voice. And this allows us to do voice interpolation or even sample new voices that are combinations of other voices. So for example, if we've got a source utterance like this, so we convert to one speaker, this is one, we do one conversion and it sounds like this.
Cabbage salad. Chop or shave fine half a medium-sized head of cabbage that has been left in cold.
And now we have a target speaker that sounds like this. In this case, we just use the same words just to kind of indicate the difference here.
Cabbage salad. Chop or shave fine half a medium-sized head of cabbage that has been left in cold water until crisp.
So that's a source and a target speaker. Now what we're going to do in this intermediary one is we're going to start we're going to say that utterance, but at the start of the utterance, it's going to be this speaker. And as the utterance plays, it's going to slowly transition to the female speaker. So if you listen, you got to catch it quite carefully because it transitions quite smoothly. So it's going to start at the male and go to the female speaker.
Cabbage salad. Chop or shave fine half a medium-sized head of cabbage that has been left in cold water until crisp, then drain.
So yeah, you can actually, take 40% of this speaker, 30% of this speaker, and 20% of some other speaker, and it'll sound quite interesting. Yeah, and essentially that is basically it. We don't need complex methods for voice conversion. Just doing k-nearest neighbors on these WAVLang features works fairly well. And we hope that this is fairly easy to use and expand upon. So essentially, here's a QR code for the demo and the code. And like a little, if you want to play around with it yourself, just scan this and you can try out the model. All the methods and code and checkpoints are all there. Yeah, that's basically it.
Cool. That's fascinating. Thank you so much. Does that mean that all of the people building all of these complex models have been kind of wasting their time? Are there any benefits?
There are benefits. So the main benefits is like here. So here, we're just showing there the trade-off of how much data you need. So on the x-axis here, it's word error rate. We want that to be as low as possible. So essentially, the lower we are here, the more intelligible it is. The more, essentially, the words are correct. And on the right axis here, this is equal error rate. We want this to be as high as possible. The higher this axis is, the closer it is to the target speaker. So in other words, the top right is where we want to be, where it's both the right words and similar to the target speaker. And the red line here is training with this pre-matching, and the blue line is without this matching. So you can see the red line is closer to the top right, so it's better than the green line. So that's why the pre-matching helps a little bit. But the key thing here is we're showing how this performance changes with different amounts of reference data. So with 5 seconds of reference here, you can see it's, a quarter of the words are wrong, just said incorrectly, and it's not super similar to the target speaker. With 10 seconds, it's still pretty bad, but it's getting there. With 30 seconds, you almost have full phone coverage, and by 1 minute, you already reaching diminishing returns. So our method needs about a minute to properly clone it, to have full phone coverage. And it gets better up to about 5 minutes. But those other methods, they work pretty well with even just like 10 seconds or like 5 seconds of reference. So they get a bit of benefit there in that it works with shorter reference clips. Yeah, that's, I guess, one of the trade-offs.
Thank you. So I think, did Myron have a question earlier?
Yeah, I did. I wanted to ask, with using your KNN equal to higher numbers, does that help overcome scenarios like problems with accents, for instance? Because I can imagine with the way the model works, accents which would have the same word but different phonetics would be quite a big problem for the model. How do you get around stuff like that?
So typically, when you do conversion with this kind of model, it actually inherits most of the prosody and the accent from the source speaker. And I think this is purely because those 20 millisecond units, 20 milliseconds is very short. I don't think it's long enough properly for accent to come across all too much. But I'm not actually sure. We haven't experimented with like accent removal or high K values. It might. It might be worth playing around a bit with it and experimenting with that.
All right. Thank you very much.
So I think if anybody working in AI in any capacity at the moment should be thinking about the ethical implications of what they're doing. And I think something like this, it's sort of very clear how it could be abused. Do you have thoughts on on the implications and applications of these methods? In some sense, the simpler they are, the more easy they are for people to just take and abuse.
Yes. So essentially, our team thought about it for a while, and then we came to the conclusion that we were going to treat it like software. So like the Linux kernel is used for, hackers, but also for all the world servers. We just released this under an MIT software license. So we treat it as a software tool that, fundamentally, as long as the users are adults, they should be responsible for themselves, and it's a piece of software. If someone wants to use it for something good, they can. If they want to use it for something bad, they shouldn't. We release it as open source software. Yeah, we treat it as code, really. So we think it should be governed similar, to the like the Linux kernel or most open source software.
I suppose, being slightly devil's advocate here, do you have a thought as to the proportion of people who might want to use it for good versus the proportion of people who might want to use it for bad, in comparison to the Linux kernel?
Yeah, I think Linux kernel has a lot more people wanting to use it for bad than these things. So we haven't seen any super active attacks with voice conversion trying to scam people for money. Text to speech is much more active, in trying to scam people where you hear random text to speech things. But in terms of voice conversion, we haven't seen many actual attacks. And the most use we've seen is for making A, assets and games cheaper, and B, making funny memes online, doing funny conversion between, different figures, whatever. But I mean, in no case has anyone ever confused I think it's very rare that someone confuses a meme, that's obviously satirical for reality. But in short, I think the amount of damage done and potential to be done for something like Python, which is the Turing complete coding language, is much greater than this, which can only be used to convert one speech utterance to sound like another speech utterance.
What's he going to ask? Oh, yeah, it's sort of in a similar vein. Can you detect that it has come out of an algorithm like this versus natural speech?
Yeah, this one you probably can. Probably it wouldn't be too tough to detect. Purely because the vocoder, the hi-fi GAN vocoder, has some telltale signs that it's so first of all, it only operates on 16 kilohertz. So 16 kilohertz is fairly low quality audio, and you'll typically hear hi-fi GAN, the vocoder here. Occasionally for high frequencies, it'll, if you have heard a few samples before and you listen to the high frequencies, you can often make out that it's a hi-fi GAN based vocoder.
Do you think there's anything to be said for what? And I'm sort of pushing here. Please do. But when one puts out a tool like this, to also put out a tool which is a sort of a detector tool to be able to test whether somebody is using your tool.
Yeah, no, I mean that would be ideal. To also have a detector to see if someone will do it. That's purely really a resource and time consideration, I think.
Sure.
And I mean, if someone had any technical skill, they could just train a different vocoder, and that wouldn't work. So I mean, there's lots of newer vocoders than hi-fi GAN. There's like Vocos, there's LPC Next, there's a couple of other newer, bigger ones. So if someone just trains, because we open source everything. So if someone just trains a different vocoder, our detection thing won't work. So it might work if someone just uses the repo exactly as is, but if someone's got a little bit of technical knowledge and just a home, consumer GPU, they can get around it fairly easily. And I imagine if someone is invested in doing something, doing a criminal enterprise, they're probably going to take basic steps to not get caught.
Any other questions?
I have a specific question about the table of results of the different methods. Firstly, the bold text is the FreeBC bold text. What does that actually mean there, to be bold?
They're the top. So what we didn't show here, just for space considerations, is the 95% confidence interval. So 95% for this just overlaps with the confidence interval for this, so we can't actually tell which one's better. But yeah, that's in the full paper. There's the confidence intervals as well.
Okay. And do you have any intuition for why some of the models do well in certain scores versus others? Just to get an idea of what this is.
So FreeBC does very well in the word error rate because it's also actually based on these self-supervised learning models like WaveLM. So FreeBC also actually makes use, I think, of WaveLM or Hubert. So that's why that WaveLM and Hubert model, they're very good at extracting phonetic information and representing them very accurately. So that's, I think, why it does very well in word error rate measures and similar in mean opinion score errors. But the your TTS and VIMC, I'm not exactly sure. They both operate in very different ways and have different strengths and weaknesses. Your TTS is a bit better than FreeBC in that it can also do text-to-speech, but in voice conversion mode, it does a little bit different. So I think your TTS is maybe a bit better in equal error rate because during training, it uses text as kind of a way to strip out source speaker information. But during inference, you just go from speech to speech.
Okay, and on that, these models are quite different structurally. I'm wondering if there's a middle ground here. I mean, has anyone tried, KNN built on top of, let's say, FreeBC to try and, let's say, bootstrap the performance here? How much does your performance of the KNN method depend on the underlying performance, and how does it scale, basically?
Yes, I mean, there's definitely a lot of work to be done. There's actually a paper published last week that builds a little model on top of KNN VC to try and alleviate these problems of that we need like at least 1 to 5 minutes to get it properly. So you can definitely, I'd say, build, try to use KNN to bootstrap these other methods. I don't know if anyone's tried to actually combine it with things like FreeBC, but the key idea is that in FreeBC, this model here is essentially replaced by a duration transformer and a large flow-based model. And in your TTS, there's also like a monotonic alignment search, if I remember right, and a couple of other models. So essentially, bootstrapping that with just K-nearest neighbors might help. I'm not exactly sure how it's work because each of the models are quite different. And on your second question about scaling, is that this model does get slower the more reference data you have, as you can imagine, because you have to find the nearest neighbor in all your matching set. So it does get slower the more reference data you have. But if you know your reference data beforehand, like say you want to do a real-time application. So this is quite fast. You can do this as real-time on a consumer GPU. But say you know your reference speaker beforehand, you have 20 minutes of reference data beforehand. What you can do is just build like a nearest neighbor index, hierarchy. There's efficient libraries for finding the nearest neighbor, lists of vectors. I think the Facebook scale repo is a very good one for that. So you can essentially do this like hierarchical matching thing, and then it's sublinear time. It's very quick.
Can you also take that? So let's say you take 20 minutes of data. Presumably, a great deal of that is going to be, the repetition and sort of subphonemes all very close to each other. Can you do a sort of a filtering where you only take, subphonemes which are a certain distance apart, so that you don't have massive coverage over one particular area?
Yeah. We haven't thought about that. That might be a good thing to try. You could definitely do that. I mean, there's nothing stopping you. Yeah, that's probably a good idea actually to test that out. I guess you could up, your K value to be really big, but just actually doing some work to make sure your matching set is very clean might actually go a long way.
Yeah, exactly. Any other questions? Cool. If not, thank you very much again, Matt. This was super interesting. I think I've certainly got a lot to think about here. I may pop you some questions at some point, and I'll definitely have a read of the paper. But yeah, thank you so much. Are you going to be coming along to the Indaba, by the way?
No, we just came back from Interspeech presenting this actual paper.
Sure.
Yeah, I just got back to South Africa a couple of days ago. Probably not.
Yeah.
But thanks very much for having me. And yeah, I hope it was at least a little bit interesting.
Super interesting. Absolutely. Wonderful. Thank you very much. Cheers, everyone.
Thanks.
Thank you.
Bye for now.
Cheers.